Hello students, welcome to this module on boundary conditions at fluid interfaces, which is part of the course CHE 614 at IIT Kanpur. Now the first few instabilities that I'm going to discuss a little later after these modules, they all relate to fluid interfaces. Okay. Sorry about this. So by fluid interfaces, I mean you may have a liquid like this, a liquid layer and a gaseous layer, or you may have two liquid layers, liquid 1, liquid 2, etc. Okay, so whenever there are two immiscible phases like gas liquid or liquid 1 and liquid 2, there is an interface that separates these two phases. Now fluid interfaces are often mobile in the sense that they are free to deform, and unlike rigid boundaries, they are very different from rigid boundaries. So we will see that most of the instabilities that occur in fluid interfaces, they crucially depend on the conditions, the boundary conditions that are applied at the fluid interface. So we need to supply boundary conditions at the location of the interface, and these conditions are slightly involved, and many of you may not be aware of these conditions. So I thought I'll spend a module or two on clarifying the basic ideas involved in fluid interfaces and their boundary conditions, how to characterize fluid interfaces, and so on. The first thing that we all know is that for rigid boundaries, we have the famous no-slip boundary condition, okay, and no nominal velocity or no penetration boundary condition. Sometimes these are combined together to be called the no-slip. Okay, so basically, if you have a rigid boundary like this, okay, you have a flat plate, and then if this is stationary, okay, now because this is a rigid impermeable boundary, okay, let's first set up a coordinate system. Let's say you have x, y into the slide or board and into the screen, and z perpendicular to the wall. Okay, so let's call this, so usually you draw a unit normal to the boundary. Okay, so let's call this n. Okay, n is the unit out normal into from the boundary, rigid boundary, into the fluid. If the boundary is flat and it is aligned along the xy plane, then n becomes Ez, the unit vector along the z direction. Okay, so what are the no slip and no penetration boundary conditions for this simple case? Now, first of all, because this is a rigid impermeable boundary, fluid cannot flow into the boundary. At the fluid solid interface, there is no fluid flow into the boundary because it's completely rigid and impermeable. So the first boundary condition, which is the no penetration or no normal velocity boundary condition, states that v dot n is equal to 0 if the boundary is stationary. If the boundary is moving with some normal velocity u wall normal, if the boundary is moving vertically up or down, then v dot n will take the normal velocity of the boundary itself. But if it is 0, then v dot n is 0. This is called the no normal velocity condition. This is basically a consequence of conservation of mass, because rho times v dot n at any point is the mass flux of the fluid. Okay, and if rho v dot n is non-zero, that means that mass is entering from the fluid into the boundary, which is not possible because we are assuming the boundary to be impermeable. Okay, so this is the normal velocity condition. This is a kinematic constraint, because this is basically a restatement of conservation of mass at a rigid impermeable boundary. Now let's come to the tangential or no slip boundary condition. Okay, so let's again consider, let's draw a boundary like this, a rigid flat boundary. Again, let's call x, y, z. Now here, of course, this is a plane, so you have to imagine like this, where this is x, this is y, and perpendicular to the plane xy plane is z, and this is the rigid surface. Now here, of course, you have two tangential directions, x and y. So if I call this tangent vector t1 and this tangent vector as t2, then the no slip boundary condition, which is not a fundamental fact like the kinematic normal velocity boundary condition, but it's mostly observed experimentally. It's basically an experimental fact, not a fundamental principle. States that the tangential component of the velocity also takes that of the tangential component of the velocity of the wall. Okay, so whatever that is. Now there are two tangent directions, so we have to write 1, 2. But if the wall is stationary, then these are 0. So the fluid sticks to the wall, and if the wall is stationary, the fluid velocity will become 0 along the two tangential directions. Okay, these are the celebrated no slip boundary conditions, although you must understand that they do not have the same status as the normal velocity condition above, because that is a fundamental fact of mass conservation, whereas this is an experimentally observed result for many fluids. So that means that there are also exceptions to no slip boundary conditions, especially in polymer melts and microfluidic flows and so on. Okay, so these are just to review what you perhaps already know about the boundary conditions at a rigid at flow past a rigid surface. Now just to illustrate, the rigid boundary need not be flat, it can be of a very complex topography as well, and at each point you have a unit normal n, and we can say that v dot n is 0, and if you define a tangent vector at for simplicity, let me assume 2 dimensions because there is only one tangent. So then we also have v dot t is 0, but n and t depend on the shape of the boundary. Okay, n is not a constant. If you have a flat plate, okay, if you have a flat plate, n is always pointing in this direction, right? N is always pointing in this direction, and t is always pointing in this direction. But if it is a corrugated or a topography that is varying in space, then n will be pointing in this direction here, it will point in this direction here, again it will point in this direction, and so on. So n is a function of the point on the boundary. That's all I want to say. But the conditions are always valid. This no nominal velocity condition and no slip condition are always valid for rigid boundaries. Okay. Now, what is going to happen for fluid-fluid interfaces? Okay. Okay. So let's first schematically draw a fluid-fluid interface, which is of course not. It can move as a function of time because it can deform at a given instant of time. Let's say this is the shape of the interface. Let ui be the velocity of the interface. That itself is a vector. So this is the velocity vector of the interface, or the velocity of the interface. Okay. Now, what is the conservation of mass condition? There are two types of interfaces. Interfaces when there is no phase change across the interface. That is, if you have this interface to be water, and if this water is also evaporating, that is a phase change that is occurring across the interface. And so there are simple interfaces where there is no phase change, and there are interfaces like evaporation of water, or melting of ice, or whatever, or condensation of water vapor to form a drop. They are all interfaces with a phase change. Okay. How does, let's call this, there are two phases. Let's call this phase 1. Let's call this phase 2. These are two different phases. Okay. Now, let me first write the condition, the mass flux condition, and then explain you what it means. Rho times u minus ui dot n phase 1 is rho u minus ui dot n phase 2. Okay. Now, ui is the velocity of the interface. Okay. So, this u minus ui, if the velocity of the interface is 0, then the mass flux is simply rho u dot n, which is what I just mentioned. But if the interface is moving at a velocity, relative to that velocity of the interface, the mass flux is rho times u minus ui dot n from phase 1. That should be the same as, because the interface by definition is a region of 0 thickness, it cannot accumulate mass. So that means that whatever comes in from this side relative to the interface must go to this side. So this is the same thing for phase 2. Okay. So you will have two different velocities, u1, u2, and so on. I'll come to that. Let me draw the vector symbols for velocities. Okay. Now, if there is no phase transformation across the interface, if there is no phase change across the interface, then what you can say is that because if there is mass flux across the interface only if there is phase change. If there is no phase change, then both these terms have to be individually be equal to 0, because there is no mass flux across the interface if there is no phase change. That means that rho times u1 minus ui dot n, rho 1 is equal to 0, and rho 2 u2 minus ui dot n equal to 0. This simply means that u1 is equal to, u1 dot n is equal to ui dot n, and from the second equation you have u2 dot n is equal to ui dot n, and if I combine these two, I'll get u1 dot n is equal to u2 dot n. Okay. this is the normal velocity continuity condition across a fluid-fluid interface. Okay, this is called normal velocity continuity. Okay, now if this is also equal to ui dot n. Okay, now again there are two possibilities. Okay, so if u dot ui dot n is 0, the interface is not moving, then u1 dot n is equal to u2 dot n is equal to 0. But if the interface is moving, there are two possibilities. Then the interface can translate as a whole. Suppose you have a drop, liquid drop. Okay, this drop can move as a whole. Okay, the interface is getting simply translated. Okay, that means that each point on the interface is moving with the same velocity, is translating with the same velocity. Okay, each point on the interface is translating with the same velocity. So that means that you can think of u dot n is equal to u1 dot n is equal to u2 dot n is equal to some constant. So we can shift the reference frame to that constant, and you can still think of in the moving reference frame, you can still make these 0 if the interface is moving with a constant velocity. But a more likely possibility for fluid-fluid interface is that u dot n, u1 dot n is u2 dot n is non-zero, but varies from point to point on the interface. So this means that each thing is moving at different velocity, normal velocity. That means that the interface is going to the shape of the interface is going to change as a function of time. We'll come to how to find the change in shape of the interface in a bit. Right now, let's go to tangential velocity. For fluid, tangential velocity continuity condition at a fluid-fluid interface. Okay, this is the equivalent of the no slip condition. This is also sometimes called the dynamic BC, as opposed to the normal velocity, which is a kinematic condition. Okay, so as I told you, interfaces are not lines like this. This is a two-dimensional representation. Actually, more realistically speaking, an interface between two liquids or a liquid and a gas can appear like this. Okay, so we'll of course put a coordinate frame. This is x, this is y, this is z. Okay, and so there is of course a unit normal which varies at each and every point in the interface. Okay, now this is the interface, which is denoted by S. So what we can say is that, and they say this is phase 1, this is phase 2. Now to find the tangential velocity, see, the total velocity vector is u in the fluid. Okay, the normal velocity is u dot n. If I multiply the normal velocity component by the unit vector n itself, and I remove that from the total velocity, that will give me the tangential component of the velocity. Okay, so what we are going to write is that u1 minus u1 dot n times n is equal to u2 minus S represents the interface between the two fluids, okay, at S. So this is the equivalent of the no slip condition for fluid-fluid interfaces. Okay. Now the shape, how now all this will now depend on what is the unit normal. How do you find the unit normal to an interface? Okay. Now let f of xt determine the shape of the interface. Let it describe the function, describe the shape of the interface. And we are free to say that, suppose I have a 3D space. Okay. Okay. X, Y, and Z, and of course the interface is a complicated shape. You imagine having a sheet which is deformed or everywhere, and you have a unit outward normal n. Okay. Now if there is a function, I can describe the shape of the interface by saying that if x vector lies on the interface, there are various points on the interface, then always the function f of x s comma t should be 0. Okay. So the interface is the set of all points xs. Okay, that is the definition of, I will find a function, and that whenever that function is 0, okay, the values of x, y, z as represented by the vector xs, now that represents the collection of points on the interface. Okay, let's take some simple examples. Let's again draw a Cartesian frame of reference. Let's imagine having a flat sheet. There is no corrugation of any sort. It is located at a distance h0 from the xy plane. Okay. So what is the equation of this surface? This surface is given by z is equal to h0. Okay, for all xy. I'm assuming that it's extending everywhere in all the both x and y directions. So let's not worry about the finite aspect of the interface, although in my schematic it appears like a finite sheet. Okay, so for all xy, I can define my function f as z minus h0 for all xy. So what does it mean? Whenever f is 0, z becomes h0, and therefore okay, so f equal to 0 means that whenever z takes the value of h0, f becomes 0. So you are locating this interface. This is called the equation of the interface for this very simple case. Okay. In general, and of course, whenever you have an interface, you are trying to write a unit normal. There are two unit normals to an interface. You can either write it like this. This becomes plus ez, or you can also consider the unit downward normal. So both are equally valid. Obviously, an interface has two surfaces. I mean, interface has two sides. If you go up, you will find a unit normal. If you go down, you find a unit normal. That also means that you can write this function as h0 minus z. So you will see very shortly that depending on how you write the functional form of the interface, the unit normal changes sign. So the unit normal has to be you first construct either this or this, and then you should stick to it. You should not change in between your calculation. Okay, so So we can say that n right now is plus or minus Ez for this particular simple case where Ez is the unit vector in the uh, z direction. Okay, so the plus or minus tells you that ambiguity or the freedom of choice you have in defining the unit normal. In general, of course, shapes are not as simple as flat surfaces. Okay, you have x, y, and z. Okay, and shapes can be quite complicated. Okay, it can bend anywhere. So this is the unit normal, and now you can define the location of the interface by a function, not just by. So you can say this is the location of this interface, z is equal to h of x, y, t. So this function this is a function of x and y and time as well, because at different times this function may change, the interface may deform. So this is given by h of x, y, and t. So the equation of the interface becomes z is equal to x, h of x, y, t, or the function that represents the interface can be written as z minus h of x, y, t equal to 0. Okay, for all x, y. Okay, so n, the unit normal, so how do you find the unit normal for this particular case? The fundamental definition of unit normal is that is the following. Suppose you know from basic vectors that the gradient of suppose I take surfaces of constant T temperature, then the gradient of temperature points in the direction perpendicular to surfaces of constant temperature. Okay, so likewise here I have a surface in which f is constant, that is the interface, which is 0 actually. So the unit normal should be proportional to the gradient of f, because that is what will point in the direction perpendicular to surfaces of constant f, which is the interface itself here. But if you want to make a unit normal, you should say that n is del f by mod del f, and because this will, dividing it by the magnitude of this vector will make it unit magnitude, and I will put a plus or minus to show that it depends on which direction you want to consider. So in some cases the context is very obvious, in some cases there is no unique choice, you have to just stick to one choice and be consistent. Okay, in some cases, for example, sorry about this, suppose I have a drop. Okay, now this is a spherical drop of oil or water or whatever. Okay, now for this the unit outward normal is defined. It's called the unit outward normal because it's pointing outside the drop, so it's called the unit outward normal. Okay, for closed interfaces there may be an obvious choice, but for open interfaces it may not be that obvious. Okay, so you have to just choose something and stick to that. Now, how do you write an equation for the evolution of the interface? The interface is evolving with time. How do you write an equation for the evolution of the interface? Okay, now this is called the kinematic condition. In interfaces, now note that f is a surface where all the points located on the interface are there, and that's how we defined f, right? All the set of points that are present on the interface lie on f such that f of xs comma t is 0. So the same set of points, so as the interface is deforming, the same set of points will lie at a later time also. So if I take the substantial derivative of f with respect to time, then I will get 0, because substantial derivative is the rate of change of anything as you follow a particle, right? Here if I follow a point on the interface and I take the substantial derivative of f as the interface is moving at a later time, this point will still remain on the interface, and as because you are following the interface itself, then its rate of change is 0 because you are sitting on the interface, right? So this is called the kinematic condition. So this means the substantial derivative is also written as plus v dot del. This is another way of writing for any material point on S. All this is saying is that at a later time, this this shape of this interface may, let me draw it with a different color. It may do like this, okay, and this point would have moved, let's say, here. And because f always contains the same set of points, if I take the time derivative of f as you follow the motion of the interface, then of course it will always be 0 because you are always staying at the interface. And so for any material point on the interface, the substantial derivative of f is 0, or it just means that if you expand the substantial derivative, you know how to write it in terms of partials and the convective term. So this is what you will get. Now this can also be written as, okay, now I can divide the entire equation by mod grad f plus v dot grad f by mod grad f is 0. But I just told you that this is the unit normal to the interface. So we have plus v dot n is 0. So what this is saying is that v dot n, if we know from the previous discussion we just had, I'm sorry, I'm flipping the symbols for velocities between u and v, but I hope you get the idea. So if you see u dot n, if it's a deforming interface, it can change from point to point. That's what we discussed. So what is this equation saying? That if I write, suppose f is z minus h of x y t, right, then df dt, z is a coordinates variable, so it's independent of time, is minus dh dt. Okay, so if I substitute this, then I take it to the other side, then I'll get 1 over mod grad f dh dt is equal to v dot n. So basically what this is saying is that the reason why the height of the interface changes in a given coordinate frame, if you remember, this is the height z is equal to h of xt, xyt. The reason why the height changes as a function of time is because if there is a non-zero normal velocity, and if that normal velocity keeps changing across each and every point in the interface, then the height will also change differentially at each and every point in the interface. So this is a very simple idea. This is almost like dh dt is equal to some vertical velocity, right? This you might have intuitively felt that if there is a normal velocity, then the height should change. This is from elementary definitions of velocity in mechanics. But because of the fact that you are doing it for a moving interface and you are moving along the interface, all these other complexities like mod grad f come. Okay, so this is called the kinematic condition. Now the next thing that we are going to discuss is the stress continuity condition. Continuity of stress condition at the interface. This is also very, very important. Okay, again I'm going to consider an interface separating two immiscible systems or fluids with unit normal n. Let the two fluids be A and B. Okay, now let me first write the condition and then I'll explain you what it means. The condition is as follows: TA minus TB, where is T is the total stress tensor of the fluid, dot N plus delta S gamma. I'll explain the symbols in a bit. Minus gamma N equal to 0. Okay. Now let me explain each of these terms one by one. T is the total stress tensor of the fluid, and for a Newtonian fluid this is equal to some viscosity times, this has the pressure part, the isotropic pressure part, plus viscosity times del V transpose. Okay, this is the total stress tensor. Now gamma is called the interfacial tension. I'm sorry about this. Okay, this is called also known as surface tension sometimes. Now this gamma del dot N, I'll show you shortly, is called the curvature of the interface. So this acts purely normally because of the fact that you have N here. This means that this will come only in the normal component of the boundary condition. It will not appear in the tangential part. So this is the fact that whenever you have a curved surface, there is an extra pressure due to surface tension, and this is sometimes called capillary pressure, right? So that is this term. Now this term appears, this delta S is the gradient along the interface. This term tells you that if surface tension varies across the interface, then there is an additional stress. It is called the Marangoni stress. Okay, we'll again come to this in a bit in more detail. So I'm just trying to clarify notation here at this point, right? So now let's first understand separately normal and tangential velocity conditions. Okay, so first let's think about normal velocity continuity. At an interface. Okay, so you simply have to take the dot product of this above equation with respect to n. Okay, if you take the dot product of this with respect to n, you'll get n dot ta dot n minus n dot tb dot n. Now this is pointing purely along the surface, so it is perpendicular to n. So if I take the dot product, you will get 0. On the other hand, this will give you minus gamma del dot n is 0. Instead of t, if I substitute minus pi and so on, okay, and this will contribute only the tangential stress balance. So the only thing that will contribute in the normal stress balance is the pressure. So you'll get Pb minus Pa, okay, and plus, I'll call this the shear stress as tau. I'm sorry, the shear stress will also have a normal component, so you'll have to write n dot Ta tau A minus tau B dot n. So these are terms of the form dv by dy and so on. Okay, that's what is the double dot product of tau with n will give you this, the normal component of the viscous stress or shear stress, viscous stress tensor. Okay, minus gamma is 0. Now, so what we'll end up with therefore is Pb minus Pa plus n dot n. Okay, and this del dot n is called the curvature of an interface. What does it mean? Suppose I have a flat surface. Okay, and if I take the unit normal to the flat surface, if I walk anywhere on the flat surface, n is always pointing in the same direction. That means that if I take the divergence, del dot is a divergence operator, so which will have the derivatives. So there is no change in n, so the derivatives will be 0. So del dot n is 0 if the surface is flat. But when you have a curved surface like a cylinder or a sphere, there is obviously a curvature, right? You associate a curvature that is measured mathematically by del dot n. Okay. Now, let's consider a sphere for example. Okay, let's consider a sphere, some let's say a drop or a bubble or something like that, and I'm sorry, you have the unit outward normal in spherical coordinates to be ER. Okay, so any vector in spherical coordinate, the unit normal can be written as NR ER plus N theta E theta plus N phi E phi. Now, because it's a perfect sphere, now therefore you'll have N theta 0, N phi 0, and NR is 1. Therefore, N becomes simply ER. Okay. Now, what is the curvature of this sphere? The curvature is defined as del dot n. In spherical coordinates, del dot is given by this. You can find from the appendices of any textbook on fluid mechanics. I don't want you to memorize this, but just be aware that the gradient or divergence operators are different in different coordinate system. Okay, so you know that for a perfect sphere, n theta is 0, n phi is 0, so you will get del dot n, and nr is 1. So I'll simply have partial of r squared, which is 2r in the numerator, with an r squared in the denominator will give you simply 2 upon r, and this has to be evaluated at the radius of the surface, because this is r is the radius of the surface, so this becomes 2 by r. Okay, so therefore if I take a stationary spherical drop or a bubble or whatever, right, then what you will find is that when it is stationary, the shear stresses are 0. Okay, by what I mean by stationary is that the shear stresses are 0. That means if you look at this expression we just had, this part is 0, so you'll have PB. What is B? B is actually in our convention, this is A, and just give me a moment. We, in our case, this is A, sorry, and this is B. Okay, so and PB minus PA is equal to, if you have a look at this expression, this is 0 for a stationary drop or a bubble, so minus gamma times 2 upon r is 0, or PB minus PA is 2 upon r, 2 gamma by r. This is the celebrated Young Laplace equation for surface tension. Okay, which tells you that if you have a drop of a liquid or a bubble of a gas in another liquid, then the pressure inside is greater than the pressure outside. B is the inside part and A is the outside part, and PB minus PA is 2 times the surface tension or interfacial tension upon R. Okay, so 2 by R is the curvature, And if I do the same thing for a cylindrical drop or a cylindrical thread of fluid, here I use the cylindrical coordinate system, but n is er again, so we'll use r theta z coordinates, the cylindrical polar coordinates. N is er, nr is 1, n theta is 0, nz is 0. So del dot n is equal to 1 by r partial r of r n r plus 1 by r partial n theta partial theta plus, okay, so these are 0. So and nr is 1. So partial r is of r is 1. So if I evaluate del dot n at r is equal to r, which is the radius of the cylindrical object, then I'll get simply 1 over r, and here if I call this as b and this as a, then pb minus pa is simply gamma by r for a cylinder, for an infinite cylinder. Okay, so this is how one understands the idea of interfacial tension in the context of stationary fluids. Of course, this is going to play an important role even in hydrodynamic stability, as we'll see a bit later. Now, the tangential stress balance is obtained by taking the dot product with for simplicity, I'm going to assume that it's a two-dimensional interface, because otherwise there are two tangents, as I've told you. So if I have a tangent t, then all I have to do is dot it with the tangent dot n plus del s gamma dot t is 0. This is called the Marangoni stress. What this says is that if I have a interface, okay, the nature of surface tension is to pull the interface, but if due to the presence of some surface active agents called surfactants, which are soap molecules, it is possible to have lower surface tension depending on how much surfactant is concentrated on the interface. That means that the regions of lower surfactants will be pulling. Here, let's say there are more surfactants, so low gamma. So less surfactants, let's say high gamma. So the interface from the pull here is less compared to the pull here. So the interface will pull, that leads to fluid motion in the adjacent fluids. This is called Marangoni flows. Okay, and this is not just due to surface active agents. You may also have temperature effects. Even variation of temperature across the interface can cause surface variation in surface tension. Okay, so these are the key boundary conditions that we will use in the following discussions on various classical hydrodynamic instabilities. I'll stop here and then we'll continue from here on in the next module.